Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am very happy to have Dylan Owens with us today. Hello, Dylan.
Hey, it's nice to chat with you.
Oh, well, thank you so much for agreeing to talk about your very lovely article. It's a great one. We'll get to it. Dylan, where are you located at?
So I'm currently living in North Carolina, in Wilmington, North Carolina.
All right. Very good. And how's the summer there in that part of the U.S.?
It has not been too bad. Trying to stay cool best I can. And given this heat, it's been a pretty hot one.
The humidity drives up pretty good there in the southeast there. So yeah. So it is August 10th, 2023 as we record this, and I'm in Phoenix, and we're definitely still in the power mode. So we're definitely quite toasty. So it's very good. Cool. And Dylan, what do you like to do for research?
So I guess going back to my time in undergrad at UNC Chapel Hill, I was doing research on exoplanets with Dr. Andrew Mann, which was really fun. I was working with time series data, trying to figure out the eccentricity of young exoplanets, which was a very cool project to work on.
Very nice.
But the paper that I'm going to be talking about today, the research that I was working on at Gemini Telescope, is about white dwarfs, specifically infrared excess white dwarfs. And yeah, trying to characterize the sources of those infrared excesses, which is what I'll be talking about today.
Awesome. Very cool. And that will bring us to this very lovely AJ article. It is open access. It's the open access era, people. You can go get a copy for free. Go get one. Disk or companion, characterizing excess infrared flux in 7 white dwarf systems with near-infrared spectroscopy. And Dylan, take us away.
Yeah. So yeah, like you just said, this paper is about white dwarf stars and or white dwarf stars with infrared excess flux, particularly these 7 systems that we observed spectroscopically in the near infrared. So yeah, I guess to just get right into it.
Alrighty.
So yeah, white dwarf stars, so they're very hot. And so given that they emit mostly in shorter wavelengths, mostly in the UV or optical, so any flux that we observe at longer wavelengths in excess of the white dwarf model, it must be coming from some other cooler emitting companion. And the 2 options for that would be either a dusty debris disk or an unresolved brown dwarf companion.
Okay. Yes.
Yeah. So I guess maybe just to say a little bit about why this is important, why this is interesting.
Sure.
Yeah, so white dwarf stars with debris disks, they can give us some interesting insight onto the composition as well as the dynamic evolution of the exoplanets that orbited the star before it became a white dwarf.
Right.
And these would be, for a debris disk, these would be planets that were ripped apart at some point after being perturbed into the tidal radius of the white dwarf.
Okay.
Yeah, so these debris disk systems, sorry.
Future solar system or something, right?
Exactly. That's what I always tell people is I'm looking at the future of the solar system.
Very good.
Yeah. So since we know that these white dwarfs are mostly made of hydrogen and helium, any other elements that we see in their spectrum, they must be attributed to something that's not the white dwarf. These white dwarfs have very clean spectra, which is very good for us to be able to find anything else. So one thing you can do, one thing you can detect is absorption lines, which would show pollution onto the atmosphere of the white dwarf. That would be indicative of an accreting gas disk around the white dwarf. Yeah, so that's not something that we spent a lot of time doing on this paper, but definitely worth mentioning and something that we mentioned in the paper.
Cool.
Yeah, so another thing you can do is you can detect emission lines from an irradiated gas disk around the white dwarf.
Right.
Right. So that's something that we did do in this paper that I'll definitely get into a lot more soon. And then another thing that you can do with these disk systems is you can estimate the geometry of the dusty component of the disk.
Right.
And you can do that by modeling the overall morphology of the flux contribution of the disk in the spectrum that we see. So that's also something that we did.
Okay. Good.
Yeah. So, and then on the other hand, looking at white dwarfs with an unresolved brown dwarf companion. So that's interesting in the sense that these are great analogs for studying hot Jupiters, and they are much easier to observe than hot Jupiters around main sequence stars, since white dwarfs are so much fainter in the infrared.
Good. Yep.
Yeah. And so these would be brown dwarfs that were probably engulfed in the star's red giant phase, which caused them to spiral inward to where they are now, which would be a close, tidally locked, irradiated orbit.
Cool. Very cool.
Yeah.
Good.
Yeah. So both of these are interesting to look at, disk systems and brown dwarf systems. And we can detect them, we can detect pretty faint traces of them as infrared excess with photometry. We're pretty good at that. But differentiating between the two options, disk or brown dwarf companion, that's difficult to do with just photometry.
Right.
So yeah, so that's kind of the point of this paper is we got this near infrared spectra of these systems, of these 7 systems.
Very cool.
With the goal in mind to characterize the origin of the excesses that we found best we could.
Good. All right. Awesome.
Yeah. So yeah, I guess that kind of brings us into
let's take a look at 7. Okay. So
yeah, so
there's dwarfs.
Right. Yeah. So these are our 7 white dwarf systems, and just kind of some overall properties about them. Things like where you find them, their effective temperatures, things like that. Yeah.
M.ca. Interesting. Okay. We'll get into that soon.
Yeah, definitely. And then this is the next table here is just like some information about our observations. I think you can hear my dog found the squeaker toy.
Love it. He likes this table a lot, so it's good.
Big fan of the observation table, indeed.
Cool.
Yeah, so I guess just like a quick summary of the observations that we did. So we did near infrared spectroscopic observations with Keck Mossfire,
right,
with Gemini Juniors, and Gemini Flamingos.
Okay.
Yeah, so we observed 5 of our systems, 5 of our 7 with Mossfire at the Keck 1 telescope in the J, H, and K near infrared bands.
Okay.
And so we observed 2 systems with Juniors at Gemini North. One of those systems we also observed with Mossfire. So that was good to get that overlapping data.
Right.
Yeah. And then one of our systems was observed with Flamingos 2 at Gemini South. So that's our only southern system, southern hemisphere system. And then we also looked at optical spectra from high res at Keck for 3 of our systems. 3 of our systems that we thought were more likely to be white dwarf, brown dwarf companions and did not already have optical observations. I think that, yes, that is in that table.
Cool.
Yeah. And we were looking for that. We were looking for absorption lines that would be an indication of like an accreting debris disk for those systems.
Very nice. Very nice. Okay. Good data set. Let's see what we got or how you reduced it, whatever you like.
Yeah. So yeah, the data reduction, not too exciting, I guess. Kind of just I spent a lot of time doing the telluric line correction, particularly. Yeah, that just involved taking our telluric standard stars and trying to fit out the hydrogen and helium lines from those stars at first, and then removing the black body curve from those spectra.
Okay.
So all you're left with is those telluric lines that you want to get rid of from your target spectra.
Right. Okay.
Yeah. So yeah, definitely not the super exciting part of the paper, but it took a lot of time to do.
Necessary. Absolutely
It's absolutely necessary.
So yeah.
Yeah. But so yeah, after observations, data reduction, I guess we could get right into the spectral feature analysis. Oh, I guess we could take a picture, look at this figure first.
Okay.
Yeah, so this was just kind of like a summarizing figure that we wanted to put in to take a look at all 7 of our systems together.
Okay.
And so yeah, what you can see here, the dark blue spectra, those are all of the Mossfire spectra that we got.
Okay, gotcha.
Yeah, so I kind of color coded here.
Okay.
And then so the dark brown here, those would be the G-nears spectra that we collected.
All right.
And then the kind of orange color there, that is the one Flamingos 2 system that we had.
Right.
So you can kind of see what I mentioned earlier about JHK. Yeah. And so overall, with all the systems, all 7 of the systems, we're trying to get just as much spectra as we could between 1 and 2.5 micron.
Okay.
That was
we got some vertical blue lines. What are those?
Yes. So those indicate the hydrogen lines that we were looking at.
Okay, very good.
I don't think, just hydrogen lines, no helium lines.
Yeah.
So yeah, those were just pointing out the passion and bracket lines that we were contending with in these spectra.
Got it. Some are quite strong, others not so much. Okay.
Yes, yeah, and we kind of make a note about that with you pointed out there with J0611.
Our one southern hemisphere one.
Right. Yeah. So this is kind of an interesting one, and we couldn't come up with, I guess, a great explanation as to why we didn't see these hydrogen lines. This system's interesting. As you can see, just the shape of it is much different from all the other ones.
Right.
So yeah, there's some interesting stuff going on with this system that could have contributed to why we didn't see these lines. Maybe some emission lines that are conflicting with those hydrogen lines in some way.
Fair enough.
Yeah.
Okay.
But yeah, a lot of the systems you do see very good, strong hydrogen lines that we were expecting to see that matched up quite nicely with the white dwarf models that we were using to model the white dwarf contribution of these systems.
Yes, I'm with you. Okay.
Yeah. So
our summary. A little bit more about the systems. Do you want to go to figure 2?
Right. Yeah. So I guess getting into the spectral feature analysis here.
Okay.
Okay. Yeah. So I mentioned before, white dwarfs. They have very clean spectra, especially the hydrogen-dominated ones that are the 7 that we are looking at. So we really only had a few hydrogen lines to contend with in our analysis. And this made it pretty easy for us to be able to detect features either from a disk or a companion. So for 3 of our disk systems, we were able to detect infrared metal emission features for the first time. Not the first time finding metal emissions at all, but the first time finding them in the near infrared. Which was pretty cool. So this was adding to the range of emissions that had previously been identified for these 3 systems in optical studies. And so, like I was saying, since near infrared studies like this are new, we had to rely a bit on those previous optical detections to help us figure out what exactly we were seeing in the near infrared. And I'd say that this was fairly successful. Actually, I think this might be a good time to go over to figure 3.
Figure 3. Let's go over to
Yeah.
figure 3. So 2 and 3. And here we go. Spectrum of near emission lines. Let's blow that up.
Right. Yeah. So this figure kind of summarizes what we found in terms of near infrared emission lines.
Okay.
There were only so there were only a couple of lines that we were not able to identify at all.
Okay.
You can see that in the other panel, right around just before 1.7 micron. Those were a couple that we weren't able to identify that we saw in a couple of our systems. But other than that, I feel like we were pretty successful in being able to identify the things we were seeing. Yeah, so for these emission features, we calculated some properties like the full width zero intensity, the equivalent width, and the radial velocity. And so kind of some, I guess, broad overview summary of what we found. So for each of the systems, we found that the things or the properties that we measured were generally consistent with the previous optical studies, which was good. We also found that the full widths values were generally consistent among each individual system. Other than a few lines that we are pretty sure to be blended with some other transitions, which we kind of blame as a limitation of our resolution in the near infrared. You can especially see that in figure 3 there, like the huge kind of blob of emission lines right around 1.2 micron, like in J0611 especially. We felt a little limited in our resolution to be able to pick out each individual transition here. But we did identify several transitions that could be blended together there.
Okay, sure. Just be washed out a little bit. Right. Oh, yes. Oh, wow. Okay.
Right. Yeah. So we found a bit of variability when it came to equivalent widths, when it came to radial velocities and full widths. And that was kind of our explanation for it, is these blended lines that you see together.
Congratulations.
Yeah, thank you.
Yeah, great.
Sorry?
Yeah, it gets a shout out. Very good.
Thank you.
Metal emission lines in the IR. Okay.
Yeah. And they're pretty strong. Like it wasn't difficult to see these. And then we just had to take the time to try to figure out exactly what they were. Yeah. And actually, I guess, so from here, if you'd like to scroll down to table 3, I feel like this would be the natural time to just mention table 3. So yeah, this is kind of where we just marked down all of the transitions that we identified as the emission lines that we observed. And yeah, this took a bit of time just because, like I mentioned, this hadn't been done before. So we didn't really have anything to look back on and say, we're expecting to see emissions here and here and here. So what we kind of did is we saw a feature that we were pretty confident was an emission and tried to figure out, based on optical studies, like probable transitions for that particular feature that we were noticing. And then we were trying to either rule it out by seeing if there were other probable features that we didn't see in the spectrum. If that was the case, then we threw out whatever candidate that would be. And this table is what we came down for. So yeah, we're hoping that this could be kind of, I guess, a reference in the future for future studies for emissions to look for in the near infrared.
Absolutely. I predict it'll get a citation or 2 or 3 or 1,000.
Yeah, that's the hope. I also thought that I should make a note about these radial velocity values. Okay. They are definitely the most varied that we found within each system. And that's another thing that we kind of just blame on our resolution and the blended nature of a lot of these lines, especially in comparison when you compare these to the previous optical studies of these systems. So we didn't do a whole lot in terms of analysis with these radial velocities, but we thought that they were worth putting in.
Putting out. Yeah, yeah, absolutely. Absolutely. Okay.
Yeah.
I am with you. Cool. Very good.
Yeah. So then, sorry.
Go ahead. No, I'm good.
Kind of switching gears over to the brown dwarf companion analysis side of things. So in terms of spectral analysis for the brown dwarf companion systems, we were looking for broad absorption features, broad absorption bands from molecules in the brown dwarf atmospheres. And so for that, our method was to remove the flux contribution from the white dwarf and then just look for these atmospheric bands that we were looking for.
Okay.
So with that, for two of our systems, two of our likely brown dwarf systems, we were able to identify a water band in the Moss fire spectra.
Okay.
And then, so this water band, and I guess, so this would probably be a good time to switch over to figure 4 here.
Figure 4, so you can go in the right way. Figure 4, here we go. All
okay.
Right.
Yeah. So in the top panel there, you can see J0052. So that is the one system actually that we saw this water band, longward of 1.3 micron. So this band is something that you would see in an M or later dwarf type. So yeah, we were happy to see that there. And then as well, we were also able to detect a carbon monoxide band longward of 2.3 micron in both J0052 and J0603, which is the second down panel there.
Yes. Okay.
Right. Yeah. And so in this figure here, you can see we've got two panels for J0603. Like I said before, we observed this with gene airs and Moss fire. And so what's kind of interesting with this, and something that I'm going to get into a little bit later in the paper, is you can see we didn't observe the carbon monoxide band in the gene airs data.
Right.
Which was something that was something that we thought a lot about, and I'll get into that a little later. But you can definitely see in J0052 and the Moss fire for J0603, the carbon monoxide band is evident.
Okay. And the curves through the spectra, those are model, those are a best fit. What are those?
Yeah, so those would be best fit template spectra from observed field brown dwarfs.
Okay.
Yeah.
Good.
Yeah. And I guess, so that's kind of a good segue into section 4 of the paper, which is all about model fitting.
And there it is. We'll get that. Table 4. Those brown dwarfs. And so we go. Where do we want to go? Table 4. Down.
Actually, you know, I think you could. This right here. This is a good figure for this.
Okay.
Yeah.
Let me blow that out a bit so we get them all.
Perfect.
Full page figure. Okay, so we'll zoom in as need be here. Right now, we're just getting a global.
Yeah, definitely. So yeah, this figure here, it kind of is a good overview of the dust model fitting that we did for all of our systems. So yeah, so to kind of just summarize this dust model fitting that we did. What we did is we assumed a disk model, a flat opaque ring of black body emitting dust.
Okay.
So the dust temperature only depends on its orbiting radius, given those assumptions. So such a disk can be described by 3 parameters, be the inner radius, the outer radius, and the viewing angle, the inclination.
Okay.
Yeah.
Sure.
And so previous studies had modeled disks and modeled infrared excess with this particular model. This is kind of the standard.
Yeah, industry. Okay.
Yeah, exactly. And there are some admitted degeneracies among these parameters. You can kind of think of, so a small, narrow face-on disk might look a lot like a very large emitting area edge-on disk. Yeah. So yeah, that viewing angle, it gives you some degeneracy among the other parameters. Because of this, we decided to try something new and develop this MCMC, this Monte Carlo or Markov chain Monte Carlo technique to kind of fully explore the parameter space of these three variables. That way we could get a probability area of the likely disk parameters for each of these variables that describe a disk. Okay. Yeah. So in this model, we just put a lower boundary on the inner radius at an extreme sublimation temperature of 2500 Kelvin. At that temperature, you expect any dust to sublimate away. Yeah. And then we also limited the outer radius of the disk to 300 white dwarf radii, which is a pretty loose constraint on the Roche limit of these white dwarfs.
Yeah, right. Okay. Okay. But this is what we did. We got inner outer. Okay.
Yeah. So we constrained our model to those, just those two constraints there. And then something that's kind of, you can see in this figure here. So we have our spectra, and then we also included Spitzer points. These Spitzer 3.6 and 4.5 micron photometry points there. Gotcha. Yes, we included those in our model fitting, just so we could better constrain the longer wavelengths as best we could.
Gotcha.
Yeah. Okay. And so, so actually, I think this would be a good time to jump into the appendix real quick, because there were a few. So if you go to figure A1 in the appendix, there were a few patterns that we noticed in our modeling that you can see in these corner plots. Yeah. So the first thing that we really noticed is the inner radius was always the best constrained parameter for us. So that would be the R in the corner plot.
Yes.
Yeah, and this was expected because our spectra is in the near infrared, which is most sensitive to the warmest region of the disk, which would be the inner radius. So we were able to constrain this parameter for all of our systems pretty well, to within just like tens of white dwarf radii.
Yeah. Okay. Okay. Gotcha.
Yeah. So then the disk inclination, the part that you're hovering over, that's where it's not so constrained as well. Yeah. And that comes back to the degeneracy that I mentioned before with the other parameters. And you can really see what I was talking about illustrated here is a large inclination, which is a very edge-on disk. That requires a very close-in inner radius and a very large outer radius, so a very large emitting area to make up for that edge-on disk. Versus the other way, a very face-on disk, you would need a smaller emitting area. So you can kind of see that illustrated here in these corner plots.
Indeed. Yes.
And then when it comes to, so that's an interesting one there, JO611. And I'm definitely going to make some notes about this one there, or that one there, because that's a very interesting system. Okay. And then, so just kind of an overall pattern with all of these systems, with the outer radius, that last variable I haven't mentioned yet. So what we saw for this, the pattern we saw for the outer radius is a peak at a smaller value, and then a really long unconstrained tail going out to larger radii. Yes. And this is also expected, just due to our lack of longer wavelength data. The coolest parts of the disk would correspond to the mid-infrared, which we didn't have a lot of data for. Yeah, and we tested this
Yeah.
this modeling scheme on a couple other systems that we did have mid-infrared data for, some far further out Spitzer data, and we found that we were able to constrain this parameter a lot better. Yeah. And then also, so if you go to the next page, this would be figure A2. So these corner plots are for our likely brown dwarf systems, whereas before we were looking at the likely disk systems.
I'm with you.
Yeah, so we ran our modeling on all of our systems, whether we thought they were brown dwarfs or disks. And we saw some kind of interesting differences between the two that you can see in these corner plots compared to the ones we were just seeing before.
Yeah.
Yeah, so for the brown dwarf systems, we usually saw a much hotter inner radius. And you can see that in the corner plots where it comes right up to the edge of our physical constraint. You can see that hard line there at the inner radius.
Yes.
These systems wanted really hot disks, really inner, close to the star. And they also wanted narrower disks with a closer in outer radius. So we actually constrained the outer radius of these systems better than the actual disk systems. So these systems wanted to be very small, narrow disks, which kind of makes sense because they're not disks, they're brown dwarfs.
Yes.
So this was kind of a cool little, I guess, proof of concept that this is kind of this would be an interesting method to use to tell these systems apart from each other, which was kind of the overarching goal of the paper, was to be able to tell these systems apart.
Right. So very good. Cool.
Okay. Yeah. I guess if you'd like to go back to figure 5, kind of just looking at the.
Let's go figure 5.
Oh, yeah, kind of there at the end.
Yeah, figure 5.
Oh, I'm realizing now I'm looking at the archive version, and you're looking. But anyway,
6 maybe.
I think it was a little higher up there. I think that was figure 5 you were just on.
Yeah, and that was for the disk. So this figure 6 here is for the
figure 6.
Yeah, figure 6. Right.
Okay. Anyway.
Good.
Yeah.
Okay. Right. So 5 was for the disk systems, and these are for the brown dwarf candidates. Okay.
Right. Yeah. So like I mentioned, actually I'm not showing the dust models in these figures, but we did run the dust modeling scheme on all of our systems. But yeah, so with this modeling of the dust proportions of the systems, something that kind of came up towards the end of this project was that we could also extend this to the gas portions. So there had been some previous optical studies that detected gas emissions that I mentioned before. And they kind of shied away from trying to characterize the geometry of the gas disks, saying that there needed to be more modeling of the disk geometry before we start making assumptions about the gas disk, just from emissions alone. So this is kind of what we did. We modeled the geometry of the disk. And so using that, we were able to make a model of the gas component of the disk as well. To do this, we made a couple of assumptions that we felt were pretty reasonable. So we assumed that the gas was orbiting the white dwarf at the same inclination as the dust, which is reasonable given formation theories about how the gases form between impacts between bodies within the disk.
Okay.
And so with that, we modeled the fastest moving inner gas radius to be half of the full width zero intensity of a given gas emission line.
Okay. All right.
And then for the outer radius of the gas disk, we derived that from the peak separation of double peaked line profiles when they were available.
Gotcha.
So we were able to do this for 3 of our systems that had optical emissions, and we opted to use the optical emissions just because they had better resolution, so they had better properties to use. And so we used these emissions and plugged in our inclination, likely inclinations. And with that, we were able to model the gas component as well as the dust component of our debris disks.
Yes.
And this worked pretty well. And I can,
Not bad.
so if you go over to table
Okay.
5, oh, sorry, table 4, actually.
Let's try up. Table 5, table 4. Oh, here we go. Best fitting of the dust with the brown dwarfs. Okay.
Right, yeah. So here we show our dust radius as well as our gas radii. And you can see, like, just for this top one, J0006, they match up pretty well. The inner radius of the dust that we modeled was right around 20 white dwarf radii.
Yeah.
Whereas for the gas, it was right around 22 white dwarf radii. So we were pretty happy with the way that that turned out. Kind of came away with that we showed that the gas and dust did spatially coincide within the disk, which was kind of what we expected given the theory behind it.
Very cool. Good. Yep. Yep.
And you're going to notice as you go through this, that J0611 that you mentioned before with the corner plot. That is the one system it didn't work too well for. You can see the gas radius as well as the dust radius. Those were very small values, unrealistically small values.
Wow.
Yeah. And that is just due to the huge amount of, or the brightness in the infrared excess in this system. This is one of the brightest infrared excess systems that we know of. And so that kind of threw our modeling off a little bit.
Yeah. Okay. So it works for most, but not all. Okay.
Yeah.
We have mystery.
So then, yeah, and then there's the mystery, and I will get into that.
I like mysteries. Okay.
Kind of switching gears though back to the brown dwarf side of things. So for the brown dwarf modeling, so before I was talking about just looking at the absorption features that we found. We also did the modeling, and maybe would you like to scroll back to figure 6. Figure 4, I think.
Figure 4. Okay. Figure 4. 2 punitive brown dwarfs.
There we go. Yeah. So this is the model that you pointed out a little earlier.
Right. Right.
So to do this modeling, what we did is we got brown dwarf template spectra from IRTF and SPECS libraries, which came out to be 325 brown dwarf templates of L and T dwarfs. And we did this chi-square type goodness of fit test with each template spectrum, where we calculated a G statistic was what it was called. And this essentially just described how well a given brown dwarf template fit our observed spectra. And a lower G value is better, which will make the next figure I'm going to have you scroll to make sense.
All right.
So if you scroll all the way to the appendix again, to figure A3, yeah, to figure A3 here. Okay, yeah. So this kind of illustrates the method that we did to estimate the likely range of brown dwarf companion. So for a given spectral type, we took the average G value among the templates that we compared, and then we just found the lower 1 sigma range among all the spectra types, which you can see as what looks almost like a water line in these figures.
Yeah.
So anything below that line would be the 1 sigma range that we would call the most likely range of brown dwarf companion. Yeah, so like for that one you're pointing at right now, 0052, we called that one don't have the table right in front of me, but something like an L6 plus or minus 3 or 4.
Okay. Mm-hmm.
Yeah, and those, yeah, we put those in table 4, but you don't have to scroll all the way back there right now if you want to keep looking at this.
Let's look at the water lines. Okay.
Yeah, so like for J0603, we did 2 of those. You can see there's the Geniers and the Mossfire. And this one's pretty interesting because they disagreed in their most likely range.
Yeah.
And so yeah, the overlapping data seem to disagree. And we had a few different theories for this.
Yeah.
This was an interesting system. Like I said before, we didn't see the carbon monoxide band for J0603 in the Geniers where we did in the Mossfire. And so this could be maybe attributed to the lower resolution of the Geniers spectra compared to Mossfire. But also what it could be is variability, potentially from viewing the day side versus the night side of tidally locked companion, which is really interesting to think about. And kind of something that hasn't been looked into too much in the past. There's some previous studies that do show highly wavelength dependent variability in the near infrared when it comes to these irradiated brown dwarfs, especially in areas of molecular absorption, which is exactly what we're talking about when it comes to this carbon monoxide band.
Okay.
An example of that would be the water band that I mentioned as well. That has been shown to vary 10 times more than the rest of the spectra around it. So these molecular bands show a lot of variability when it comes to day side versus night side. There hasn't been a comparable study for the carbon monoxide band, but in photometry, the K band, which is where this atmospheric band is located, has been shown to be highly variable.
Okay.
Yeah, so some time series infrared spectroscopy would be really interesting to get for this particular system to see how that carbon monoxide band is variable, or if it is at all.
All right, we'll come back to that point. Okay.
Definitely.
Good.
But yeah, I think that is everything I had to say about this technique here that we used. I guess just to give like a quick rundown. So or if you look at table 4.
Table 4. Let's go to table 4. 5 and 4. I'm just fitting again. Okay.
Right. Yeah. So our 2 likely brown dwarf systems, J0052, we found that to be an L6.5 plus or minus 4 as the spectral type, is the most likely spectral type.
It's in the pool.
And then for J0603 that we were talking about, for the Mossfire data, we found it to be an L3.5 plus or minus 3.5. And then the Geniers was quite a bit different. It was it was a T 2.5 plus or minus 2.5. So the Genier spectra seemed to favor a later spectrum type. Yeah. So
very cool.
Yeah, that kind of goes over all of the analysis that we did. I guess this was kind of getting into the discussion.
There's lots of nitty gritty discussion on each system. It's really cool. So
yeah,
we don't have to cover that here, but I just want to remark on it, right? There's lots of juicy detail on each of the individual systems, and I encourage people to take a peek. It's very cool.
Yeah. Well, I thought that I would just highlight a couple of interesting things from that discussion, a couple of the more interesting of the 7.
Okay.
The first one would be white dwarf 0145.
0.5. Let's take a peek at one of those. 0145, 0145, 0145, 0145.
Perfect. Yeah. So this system's pretty interesting. For one, so this was the only dust disk system that we did not identify any emission features for. And this actually wasn't super surprising for us. because in optical studies, it only showed weak calcium emission, but that is one thing that made it stand out.
Yeah, certainly.
The really interesting thing about this system, though, is that back in 2019, it was discovered to be going through a mid-infrared burst where it got brighter by about a magnitude in the mid-infrared while staying about the same in the optical. And this was attributed to a planetary body being tidally disrupted in real time. So because of this, our best fitting disk model had a bit of a tough time reproducing all of the photometry. And we think that's just because of variability, the time between different observations.
Sure, if it's undergoing an outburst, it's variable.
Yeah.
Pretty cool.
Yeah.
This is.
I think that.
Yeah.
Yeah.
Very good.
Exactly. Yeah. So then another interesting system that I already talked about a bit is J0603, which one of the brown dwarf systems. This is the one that we had overlapping data that conflicted a little bit. Yeah. And so, yeah, I guess like I was saying before, about the variability, that's kind of a interesting theory about what we could be seeing there with that band head.
Yeah.
And although we spent a lot of time trying to figure out the conflict between these two instruments that we observed it with, we still did feel pretty confident, very confident that this was a brown dwarf companion system, kind of keeping our overall goal in mind to differentiate between the disks or dust.
Indeed.
So then another interesting system to highlight, J0611.
611.
Yeah, so this was our only Flamingos 2 target.
Yeah, that's only
exactly, only Southern Hemisphere. And so, yeah, like I was saying before, this system is really interesting because of how bright it is, how bright its infrared excess is. It's one of the brightest known. And actually, if you go to the figure, I think it's figure, sorry, if you could scroll up a little bit, I can probably see.
Dwarf companion.
I have the archive. It's figure 6, I think.
That would be down. Yeah, let's try figure 6. Let's go back. Figure 6. Let's try 6. Figure 6. These are the two brown dwarfers. And no 611 there. No 611 there. So let's go to figure 5. 611. There we go.
That's the one. Yeah, so I thought it would just be good to look at this, the brightness in this, and how steep its excess is climbing, going out to longer wavelengths.
Right.
So, yeah, our flat opaque disk model was not able to reproduce this very well at all, and we tried relaxing our constraints on the model. We kind of just let the model do what it wanted to do, and we still weren't able to reproduce this amount of excess. Essentially, what this system's going to need is a more complex model with several dusty components to properly reproduce all of the excess that we're seeing here.
Okay.
Yeah. So yeah, that was just one that stands out.
Oh, no, it was totally different than the other ones. So yeah.
Yeah. So then, other than that,
hey, how you doing there with that toy?
then the last one I was going to highlight is the mystery system. It's the one system that we weren't able to figure out whether it's a disk or companion. This is J0723. That would be over in figure 6, where we show brown dwarf models as well as the dust model. We show them both, and yeah, it's the bottom panel there, figure 6.
Yep.
So this was a real mystery for us. In our optical high-res spectra, we didn't detect any pollution onto the white dwarf atmosphere. Okay. We put an upper limit on the accretion from that high-res spectra. And so if this is actually a dust disk, it would be the lowest mass accreting dust disk ever found, which kind of leaned us in the direction of a brown dwarf instead. However, you can kind of see this here. We didn't find any emission features indicating a disk or the broad absorption features that we were looking for to indicate a brown dwarf.
Yes.
So we didn't find either, which was real puzzling for us. We went back and checked the Spitzer images for potential background galaxy, which could be spurious, a spurious excess.
Yes.
We didn't find anything there either, which is not to say it's impossible that it's not there, but it wasn't something that we were able to find. So this one remains a mystery, which, yeah, more observations potentially could shed some more light there.
Very cool.
So yeah.
Well, with discovery sometimes comes mysteries, and so that's
definitely
good here. So very cool.
Cool. And those were all of the highlights that I had to make from the discussion section here.
Right.
I'm glad to hear that you appreciated each individual system getting its own time to shine,
so to speak.
Yeah.
Very cool.
So yeah. I guess just like a quick little conclusion here. Yeah, we observed these 7 infrared excess white dwarfs. And we were able to determine the source of excess for 6 out of the 7.
Right.
In 3 of our dusty debris disk systems, we were able to identify near infrared emission features from magnesium, iron, silicon for the first time. And in all of those systems, we modeled the geometry of the dust using that MCMC technique.
Yes.
And with that, we were able to extend it to model the gas component as well. And then for 2 of the systems, we confirmed the presence of 2 new white dwarf, brown dwarf companions, right, as the source of infrared excess. In those, we were able to identify absorption features from molecules in the brown dwarf atmospheres. And we were able to estimate the likely companions for each of those systems. So yeah, that's kind of, I guess, everything I think I had to say.
Very nice. Well, at least for now. Very nice. Dylan, I want to thank you so much for walking us through your very awesome AJ article. Very cool.
Yeah, thank you.
Let's see. And you mentioned it a couple times, or hinted at it a couple times, and so let me push on that a little bit. So where do you think we go, let's say, over the next 2 to 5 years? Are there additional single shot observations, maybe at other wavelengths, to fill in some of the gaps that were in some of the spectra? Is there programs to do time variability at some particular cadence? Is there additional theoretical work that could be done? Just sort of, where do we go next steps over the next couple of years on this topic?
So I'd say, I'm probably not the first person to say this to you, but more observations, I think, would be the way to go.
Okay. But which kind would you? Okay, so given your choice, would you rather fill in the gaps in the spectra you got now, or would you rather have it go after the variability?
So I guess I would say,
don't say both.
I guess depending on what we're looking at. So for the dust disk systems, yeah, I would be really interested to be able to get longer wavelength data for those systems. Specifically looking at James Webb to get that
hey, there we go.
longer wavelength data. That would really help us, our model, constrain the outer radius, especially of the disk, which would in turn also help us constrain the inclination. So it would make our modeling a lot better having that longer wavelength data. Yep. Then switching over to the brown dwarf companion systems, okay. I talked about this a little bit before, like you mentioned, some time series spectra, especially for that one very interesting brown dwarf companion that we saw, where the 2 spectra that we got conflicted. It'd be interesting to see if we can pin down exactly if we're actually seeing variability, or if there's some other explanation for why those 2 spectra were conflicting.
Yes. Mm-hmm. Very nice. Well, I really look forward to seeing this topic evolve over the next couple of years, and there's more observations coming in, both static at longer wavelengths, and let's do a time variability survey on a couple of these interesting systems. So very nice. Thank you so much, Dylan.
Yeah, thank you. Thank you for going over this with me.
Pleasure. And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.